Okay, so welcome back to our Thursday morning session. At least it's morning in Berkeley, so it's nice and shiny here. Our first speaker is Oleg Chalykh from University of Leeds, and he'll be talking about twisted Ruijsenaars model.
Thank you. First of all, thanks to the organizers for the invitation to speak here. So I will be talking about some deformation of the Ruijsenaars model. The parameter of deformation will be discrete, just an integer. So here's a plan. So I will remind you very briefly what the Ruijsenaars model is. Of course, everyone here knows that. And then I will show you an example of the deformed one in the simplest non-trivial case. And then I will explain several contexts in which this kind of integrable system appears. So the first one is it goes back to our paper with Ettinger, and this is the integrable system appears from the theory of Baker-Hazer functions in McDonald theory. And then the second approach is through Hamiltonian reduction on some multiplicative quiver variety for the cyclic quiver. And this is this was done in our work with Maxime Ferrand, and this is just for the classical case, for the classical system. And then there is also a third approach using cyclotomic daha. This is due to Braverman, Ettinger, and Finkelberg. And then towards the end, I will talk about the fourth approach, which uses elliptic Chalykh operators. So this works in the elliptic case specifically. Okay, so let me start by reminding the Ruijsenaars model in the trigonometric case. So it's given by these Q difference operators. So this T here is multiplicative shift. Okay, the notation is explained here, and summation is over subsets of cardinality K. So the simplest Hamiltonian is H1, but altogether you have n independent commuting quantum Hamiltonians, and so here's H1, well known. So this integral model goes back to Simon Ruijsenaars in the quantum case, and in the classical case, usually is referred to as Ruijsenaars-Schneiden model. And these Hamiltonians written in this form, they're actually a special case of what is known as Macdonald operators. This is type GLN. Okay, so that's a quantum integrable system which we want to deform, and main result is that for any integer, there is a completely integrable model whose Hamiltonians are, roughly speaking, the L's powers of those HKs. Okay, so this is not a kind of an exact statement, right? So you cannot call it a theorem because I don't explain what this means. But nevertheless, that's the idea. And these Hamiltonians are quite complicated. And as I mentioned, first implicit construction goes back to our work with Pavel. And I will show you one example where I can write it completely explicitly, one of the Hamiltonians, and that's this calculation was done in our paper with Maxime Ferrand, and this is when L is 2. So the simplest one will be H1 tilde. So as I said, it roughly looks like the square of the first Hamiltonian for the Ruijsenaars model, and if you square, then you expect the these Q shifts, you get squares of these Q shifts, but also because you have these cross terms, you expect it to have this shape, and the leading coefficients AI look like this, and then the coefficients Bij are more involved, and here I put them together. So in the red box, so on the left and on the right are two cases. The non-deformed case is on the right. So that's how the coefficient would look if you just square H1. And on the left is this coefficient for the twisted case. Okay. Right.
So by squaring, you mean if you take H squared and do the normal ordering, put the difference operators to the right, that's what you get, right? And then
yeah, yes. If you push all the Q shifts to the right, yes, that's what you get. Yes.
Or the xi's are commuting variables.
Xi's are commuting variables. Ti's between themselves they commute, but yeah. Okay, so.
Sorry, Oleg. So you are going to have square roots of xi, yes?
Yes. Well, these are exponential coordinates, so it's kind of harmless. But in fact, you can get rid of square roots by conjugating by certain Gaussian. So later it will appear in different form without square roots.
But this appearance of square root corresponds to the choice of L equals to 2 or not?
Yes, so 2 corresponds to L, yes.
Okay, good, thank you.
Okay, so so the first approach through Baker-Archer functions. So these are Eigen Functions for the Ruijsenaars model. So in Peter's talk today, he considered rank 1 case. Basically, it's equivalent to 2-particle case of Ruijsenaars model, and he mentioned that eigenfunction can be written in terms of the hypergeometric series, but for special parameters like this, the eigenfunction actually is an elementary function, and so it's not directly related to Macdonald polynomials. It is quasi-polynomial because the spectral variable lambda here could be is continuous, not can be arbitrary, not necessarily those discrete values for the Macdonald polynomials. Okay, so it's like a kind of like Bloch solution or quasi-periodic solution, and this function being elementary is not trivial, nevertheless, and has a number of remarkable properties. So in particular, for instance, one can recover most of the main results about Macdonald polynomials by studying just this psi and
yeah, exactly. So this truncation phenomenon is relatively new, and I think it still needs to be explored more. So there's many interesting connections there. Yeah, I agree.
Right. So it's but it's not symmetric, right? So that's the difference. I think the one you wrote was automatically symmetric already and truncates to polynomials, to Macdonald polynomials.
Yeah, that's right. And I think my normalization was a bit different than from Macdonald's book, but I chose a different prefactor, I think.
Right. So it's different truncation to the one, yes, you can see it, I guess. So this, but this case, I think, also appeared in your as one of the cases.
That's right. That is correct. Yes.
Right. Okay. So, by the way, in this case, the usual Macdonald theory has problems because you will have poles in the. So the measure, which usually you consider, would have poles on the torus over which you integrate. So, so for strictly speaking, for this value of t, Macdonald polynomials, not all Macdonald polynomials are well defined.
Right, but I think in my case, if the j label is less than m, then it's okay. So like it's if you don't hit the pole, then they exist. I think. Yeah.
right. So some of them are defined, some of them are not well defined. Yes, and there are issues with the inner product. If you use the Magnolet inner product, it's not positively definite. Right. Okay. So this function then has a remarkable kind of self-duality with respect to if you integrate against Gaussian. So that's the result from our paper with Pavel. So the integration here, so the measure has this product which is kind of similar to the measure you see in Magnolet theory, but because t was Q2 negative integer, it goes to the denominator. Okay, so as I mentioned, there are singularities, and well, maybe some of them, maybe there are no singularities on the real torus or imaginary torus, depending how you look at it. But still, if you integrate just so here, what I'm doing, I shift the integration contour. So if you can integrate in principle in this case just over the imaginary space, if I'm not mistaken. Yes, this would be fine, but this integral wouldn't have correct properties. So the trick which we borrowed from the paper with earlier paper with of Pavel with Parchenko. So uses this idea that you should shift the contour, and okay, and then if you shift it far away in a suitable sense, so I'm saying here, explaining here, if psi is large in this sense, so far away from the walls of the wild chamber, then what happens is that the value of this integral, you get back psi itself with the Gaussian prefactor. Okay, so it's kind of self-duality with respect to this integration. It's like this basic result in Fourier theory that Gaussian is self-dual with respect to the Fourier transform. Okay, so and then by just thinking about the proof, the way we prove that, you realize that you can do something slightly different. Namely, instead of the usual Gaussian, you put L here, integer L, and still the integral you can show that it's kind of computable. It's an elementary function, and so this is a way to define this twisted Baker-Hazer function just by using this integral formula. Okay, and it still has. So as I said, it's an elementary function, so it's kind of quasi-polynomial, and then you can use kind of indirect arguments similar to this finite gap, so-called Cauchy-Ware argument from finite gap theory to show that this psi will be eigenfunction of commuting difference operators. Okay, so this is implicit indirect construction of this integrable system. We first construct the eigenfunction using this integral formula, but not the Hamiltonians themselves. Okay, right. So this was fairly implicit, and the second approach.
So at this point, L can be any parameter, even complex, right?
No, it's important for this to work, for this formula to give elementary function as a result. L should be integer.
Oh yeah, otherwise you're not going to get the truncation. Yeah, okay, yeah, like the plane.
Okay, so yes, so the second approach is through Hamiltonian reduction. I'll just here recall briefly. Again, we saw it in Peter's talk yesterday. So this is the way to get classical, so Ruijsenaars-Schneiden model from the representation of certain quiver. This is shown here. So where the space of representations of this quiver, so these are two vertices. You put one-dimensional space here, n-dimensional space here. So in Peter Stork, n was 2 here, right?
Yeah, that's right.
Mm-hmm. Right. So so this is rank n, and this is so-called Calogear-Moses space from Oblomkov's paper, and but it was known kind of to Falk and Rossley before. So that's sorry, I'm saying here something different. So it's just a classical, usual Calogear-Moses system. This is Kazhdan, Kosten-Sternberg approach how to get classical Calogear-Moses system by considering matrices. So the cotangent space to this space, and the moment map looks like that. I'm very brief, kind of. So it's an overview, and then you fix the value of moment map to be identity, and doing Hamiltonian quotient, you get a phase space of dimension 2n, and that's how you get the Calogear-Moses system, by doing this Hamiltonian reduction on this space. And now to get a Ruijsenaars model, you can do either Poisson reduction according to Falk and Rossley, using different Poisson structure to the standard, to the canonical Poisson structure on the previous slide. Or alternatively, you can use quasi-Poisson reduction, and then the moment map, so-called multiplicative moment map, and given by this formula in terms of these matrices xy and vector covector VMW. So if you fix these to be identity or multiple of identity, then that's exactly, if matrices are 2 by 2, that's exactly the this space Peter talked about. VW is just a matrix of rank 1. So this is the semi-simple element corresponding to holonomy around the puncture on the torus. Okay, and but in higher rank, okay, so it's this quasi-Hamiltonian reduction on the fixed, when you fix the value of the moment map, gives you Poisson variety of dimension 2n, and that's a particular case of the multiplicative quiver varieties, which were introduced by Crowley, Bovie, and Schur, and then Vandenberg explains how you can do quasi-Hamiltonian reduction to get these varieties. Okay, so that's how you get classical Ruijsenaars-Schneider system on this space, and maybe I'll skip the details. So you can introduce coordinates on this space, and then you parameterize matrices x and y explicitly in terms of local coordinates, and then the Hamiltonians of the Ruijsenaars system are just traces of the powers of y, and you can recover the familiar formulas from that. Okay, so that's a well-known story. Now you can do the same for the cyclic quiver. Here is a picture with 4 vertices. You put n-dimensional space at each of them. Again, you have framing with VNW, and the group which acts on the space of representations is just the GLN raised to L, and it acts by changing basis at the vertices. And again, you can do quasi-Hamiltonian reduction. Moment map has several components, and so this follows the kind of the Vandenberg's approach, and you get these formulas for the components of the moment map, and you fix them to be multiples of identity, and as a result, you get 2 n-dimensional smooth symplectic variety. But it's a somewhat kind of limited case of the multiplicative quiver variety. So it turns out that in this case, this although you have these L parameters at the vertices, actually everything essentially depends only on one parameter, which is the product of these T's. So it's a kind of, it's a simplification of the story for the full story for the cyclic quiver. Okay, and then the natural Hamiltonians, which you can take, are traces. Now, instead of one matrix A, one matrix Y, you should go around the cycle, around the loop in this cyclic quiver, and get the product of these Y's and take in arbitrary powers. Okay, from 1 to n, you got commuting Hamiltonians, and that's an integrable system. And again, you can calculate how these Hamiltonians look in the coordinates, but the phase space in this simplified story is that you can actually, by using the action of the Lie group, you can make almost all matrices X to be just identity, and you are left with just one X, and essentially just one matrix Y. So everything is parameterized by just a pair of matrices X and Y, and they satisfy the same relation as we saw in the for the tadpole quiver. So it's so this phase space actually is the same phase space as for the usual Ruijsenaars system, but the integrable system is different. Okay, so the same phase space, but remember the Hamiltonians of the Ruijsenaars model were traces of the powers of Y, but here you got traces of, if you do calculation, you get expression like that. So it's so Y is like Lax matrix for the Ruijsenaars model, but then you raise it to power L and then mix it with X inverse. Okay, so that's the twisted Ruijsenaars Schneider system. It depends on L, and maybe a remark on this phase space of Ruijsenaars Schneider model. There are various symmetries like that mapping class group action, which Peter mentioned yesterday. So one of them is so-called Ruijsenaars duality, and under this duality, these Hamiltonians of this twisted system become these ones, and these are much simpler actually. If you write them down, well, here is one of them. It's basically the same structure as the Ruijsenaars Hamiltonian and just powers of the coordinate in front. So these kind of operators appear particularly in works of Di Francesca and Cadden. Okay, so these are fairly simple to write, but these are fairly complicated. But they're doable, and the same is true on the quantum level. So these are actually quantum, as written here. Okay, and yes, and now the third approach is through cycloatomic dahas. So that's these were introduced by Braverman, Ettinghoff, and Finkelberg, 2016, and again, it's a brief recall of the well familiar setup. So daha of GLM type, it contains two commutative subalgebras of Laurent polynomials in n variables, x and y, and there is also underlying this, there is a Hecke algebra of the symmetric group, and so the parameter t enters these Hecke relations, and but plus there are also braid relations, and there are also relations between x, y, and t, and q will appear in some of these. So there are q and t, two parameters, and it has a representation, sometimes called Dunkel representation, in terms of difference reflection operators acting on n variables, and they're given by some explicit formulas for the generators, but basically x are just functions, and ti's are given by explicit formulas like that, and so they involve reflection, which Si, which is just elementary transposition, and you can see you can think of these operators as acting on functions of n variables by permuting the variables, and then y in this representation are much more complicated, but given by some products of t's and suitable pi. Okay, I'll just skip the explaining all that. It's well known. Daha of type GLN, and then what Finkelberg defined. So given an integer L, they define a certain subalgebra inside this Daha. Again, I will not give the definition, but only part of the results which is relevant to our to this story. And so what you do, so inside this, so the usual Daha related to Ruijsenaars integrable system, and this cyclotomic Daha is relevant for this twisted Ruijsenaars model. So to construct the twisted Hamiltonian using this approach, you consider these quantities di upper L. So some product formula in terms of the generators of Daha, but I'm just stressing that this combination, which we saw before in this quiver story. So you have this X inverse and Y2L. Okay, and so then they show that these elements commute, and then you take symmetric combinations of these T's and restrict them to symmetric functions, and that's the kind of standard way of obtaining obtaining difference operators. So by restriction, you get rid of the reflections of the permutations. Okay, so that's an integrable system which is part of this cyclotomic Daha story, and they show. So if you just look at this, you don't see directly a relation with this approach from Baker-Heser functions, but they explain actually that they coincide with the quantum Hamiltonians from the first approach, and in the classical limit they also explain the relation to quiver varieties, and so in the classical limit you get those Hamiltonians from the for this multiplicative quiver varieties for the cyclic quiver with L vertices. Okay, so but this story, their story actually is more general than this. Again, it's a kind of limiting case of the approach. Their cyclotomic Daha actually involves L parameters sitting at the vertices of the quiver, like those T1, T2, and so on, TL, which I had in this quiver picture. So they're essential parameters in general. But here I'm taking the limited case.
And Oleg, they really are T inverses on both sides of your X1 inverse Y1 to the L, are they?
Yes, I think so. Well, it's we've been asked to give informal talks, so I haven't.
Yeah, it's just puzzling. It's just puzzling. That's all.
Right. Well, I think that's correct. Yes. Okay. But you should take everything here with a pinch of salt, and yeah, there could be some typos, but I think that's correct. Yes. Okay. And now, yeah, I have time. Yeah, right. Okay. So now I'll explain the elliptic version, which I expect to be related to these trigonometric integrable systems, but this hasn't been checked carefully. Okay, but I will explain that there is some similarity of what I will do with what you saw before. Okay, so elliptic integrable system will be, let me first recall how one can construct elliptic version of the Ruijsenaars. I think I skipped, yeah, accidentally skipped this slide. So now we're talking about.
Excuse me, Oleg. So can you summarize the first parts of those functions psi in the when you truncate them, right? So they are again functions of twisted RS Hamiltonians, right?
The twisted version of these functions. So not the original psi, but after.
Yeah, the twisted with this L. Yeah.
Yeah.
And then is there a generic statement like on the level of hypergeometric series, like the without truncation? This hasn't been done as far as I know. I see. Okay. Yeah, I would expect to have similar result there too. But yeah,
so the relation of these to this hypergeometry, including this elliptic case to the elliptic hypergeometric function, hasn't been explored.
I see.
It's an interesting question. Right. Okay. So this because you yes. Okay. Right. So now we move to elliptic case because of this well-known kind of triad of rational trigonometric elliptic in this integrable system story. You expect maybe there should be an elliptic analog of that integrable system. And so let me first recall how the elliptic Ruijsenaars model can be constructed. There are several ways of doing that, but the one I need follows Kamori Hikame's paper. And so let me, so this is the Ruijsenaars Hamiltonian, the simplest one. So this sigma is this particular combination of theta functions. In Andrei's talk yesterday, we saw it a lot. So theta is odd theta function, and so mu, the parameter mu here plays the role of the coupling constant. In Macdonald theory, that was T, and beta here. So this exponential is just a multiplicative shift. So e to beta plays the role of q. Right. So this is an integrable system, as was shown by Simon back in 80s. And but the construction which I will talk about is different to the construction to the direct construction of Ruijsenaars. So we will use elliptic Cherednik algebra. So in that sense, it has some similarity with the daha approach, but there are some differences as well. So, but indeed, trigonometric operators can be recovered in the trigonometric limit when you take the period of your. So this theta function is with periods 1 and theta and tau. And if you take tau to infinity, then and think of e to mu as t and e to beta as q, then you recover actually the trigonometric Ruijsenaars model with parameters q and t. Okay, so now how to construct these elliptic difference operators. We need these R matrices. Well, these are not matrices. So in type A, they go back to Shibukawa-Yana, and these are the following elements. So here you have functions of x. Sij again acts on functions of x1 to xn by commuting variables. Now the first term here dependence is upon this coupling parameter mu. In the second term, you have this difference of psi I minus psi j. So psi's here are auxiliary variables. I will call them spectral variables. Sometimes they're called dynamical, but This is probably a bad name because this R satisfies the usual Yang-Baxter, not the dynamical Yang-Baxter relation. So they are not matrices, they act on functions. So sometimes people call them like infinite dimensional R matrices or functional R matrices. Right, okay, so that's the gadget we will use. And then you construct, so this, on this slide, I will only use Y1. So the first of these, so there are elliptic Cherednik operators. So in the dahas story, you have Y1, Y2, and so on, Yn. So they exist here as well. And so I need only Y1 to construct the first Hamiltonian. You get this combination, you take this combination of R matrices, which is familiar, might be familiar to you from the QKZ equations or integral lattice models. So you take this and followed by the multiplicative shift. Okay, and then so this is, if you imagine you expand all these, you get lots of these terms, you get lots of terms. There are these Sij's in various combinations. So it's a reflection difference operator as such. So the claim is the following: if you now take these spectral variables and specialize them to specific value, so this vector rho is the half sum of the positive roots, and mu, remember, is a coupling constant. So the theorem of Komori and Hikami is that if you specialize psi, then this operator Y1 will become symmetric. It will preserve symmetric functions, and if you restrict it onto this space, all reflections Sij's can be absorbed, would disappear, and you get just the honest difference operators with elliptic coefficients, and this will be the first Hamiltonian of the Ruijsenaars model. Okay, so that's the construction. If you compare it with daha approach, it looks a bit strange at first, because in daha you take Y1 plus Y2 plus Y3 and so on plus Yn. But here you don't need to do that. You take only Y1. But it's not exactly the same as daha, because there are the spectral parameters, spectral variables, and you don't have them in the usual daha story. Okay, so that's the difference. And at first it looks a bit confusing. Only the shift in the first variable appears here, but of course when you restrict onto symmetric functions, you have to push all the Sij's, to the right, and so in particular these shifts will change to shifts in all possible directions. So this restriction produces actually an operator where the shifts will be not only in x1 but also in all n variables. Okay, and higher Hamiltonians can be constructed similarly. And what is very nice about this approach, it works smoothly for all root systems, including the BCN case of Van Dien system. Okay, and now I will just I have time just to explain construction of the twisted model in this using these ingredients. This is working in preparation, and so you take Y1 as before. Remember, it involved these auxiliary parameters psi. Now the parameter of deformation will be a point C on the elliptic curve. It will be a torsion L torsion point. So so C is such that LC is just the integer combination A plus B tau. Okay, and then we define a twisted version of this operator Y1, in the following way. So you take a product of y's, appropriately shifting the spectral variables in the direction of E1. Okay, so you should by C here, eventually by C times L minus 1. And at the end, you put this exponential. So B is just this, the tau component, the integer entering into this formula. Okay, right. So, and then the theorem is the same, roughly, is that if you now consider this Y1, specialize the spectral variables to this specific value, then this operator preserves symmetric functions, and if you restrict, you get an integrable system. So there are higher order Hamiltonians, and they commute. Now, why I expect this to be related to the trigonometric case? Well, it's kind of not very precise, maybe, but you can take trigonometric limit if you choose C to be tau divided by L, and then let tau go to infinity. Then this in this limit, this dependence on psi becomes disappears. So actually, all these the way that the fact that you shift this doesn't matter, and this y1 becomes just the power of y1 as we had before, and then followed by this b is 1 in this case. I'm talking about this particular choice. So it's just e2 minus 2 pi I x1. You can call it x1 in the daha setting, and so that's
so it looks like in a Zemtsov, but it's not, right? You don't get any Toda-like system. You rather have this like those shifts, as you said, they don't matter. They would
yeah, that's right. So no, it's really the deformation of Ruijsenaars system, right? So it has again, it approximately has the same shape as y raised to L. So it's like L's power, so L's power of the first Hamiltonian. Okay, and the higher quantum Hamiltonians construct similar. You just consider this apparatus Y for the fundamental weights, or core weights, and then you take a suitable combination of the R elements followed by the shift, and but then you do the same. You construct this twisted version by taking the product of these Y's, where you shift in the direction of this fundamental weight. And here it will be not just x1, but x1 plus x2 up to xk. And the same thing after that. You set the spectral variable to special value and restrict them to symmetric functions. Okay, so that's the construction, and this works also for in a similar way to other root systems, including the Van Dien system. The existence of integrable system, this twisted version of Van Dien system, was conjectured by Harry Kranz in his paper on the elliptic dahas. So in particular, this gives a construction of that integral system conjectured by Rains. Okay, so I think that's all. Yes, thank you.
Thank you very much, Oleg, for a clear talk. Questions, please.
Can I ask a question, Oleg?
Yes, sure.
So regarding this conjecture of Eric Rains, so Eric constructed these elliptic dahas, and I presumably they contain commutative subalgebra, which gives such system. Is this what happens?
Yes.
Mm-hmm. So he could not show the existence. So he would not show some flatness. Yes, is that why he made a conjecture rather than theorem? Or
no? As far as I understand, the problem was to construct sufficiently many elements in this spherical daha. So it was. You need to count how many sections you get, and so
yes,
the problem was there.
Okay. So he gave a conjectural description of it, but he could not show that it is big enough. Yeah.
Yeah, exactly.
Mm-hmm.
So when L is 1, it coincides with the Van Dien system. I think he explains that in the paper. But because construction is different, it's not. You need to probably to show that you need to go to Van Dien system, look at the higher Hamiltonians, and establish some properties, kind of residue conditions of the coefficients, something like that. So it's. I don't remember whether he fully checks this in his paper or not, but it can be done. But for higher L, it wasn't clear.
And also in this paper with Finkelberg and Braverman, we described this Q-deformed cycloatomic daha, which contains this integrable system as a equivariant K-theory of some kind of infinite dimensional space. And if you take elliptic cohomology, do you expect to obtain this Eric's algebra?
Right. Well, good question. But I have no answer.
Which space is that, Pavel?
So this is a space of triples. It's called space of triples. So it's some kind of well, I mean, it's defined, I think, by Braverman, Finkelberg, Nakajima.
So it's a quantized, well, K-theoretic Coulomb branch, right? That's what.
Yes.
Okay. And then I see it. Then you ask me if you upgrade it to elliptics, then maybe you get Rhine's algebra. Okay.
Is it known or is it a conjecture?
No, I haven't. I don't know. Yeah, maybe not. Other questions? Yes, we have time. I don't see our next speaker yet, so.
Well, maybe I can ask about the eventual existence of deformed twisted R models. It's already bad enough to be twisted and deformed, but maybe it can be done.
Okay, good question. You mean those deformed, like the ones Hjalmar was talking about?
Exactly.
In that paper with Pavel, well, in the appendix, I checked that it exists for one special case when you have just n particles in one group and one particle in another. In that special case, yes, at the trigonometric level, such thing exists. So I would expect them to exist as well for the deformed cases. Yes.
Okay. Well, thanks.
But
I mean, they are obtained from some special representations of the Chalykh algebra, right? And these representations, we expect them to deform to all these cases, right? Because this deformation at the level of abstract deformation theory are trivial somehow.
You mean in the trigonometric case, right?
Yeah, also in elliptic case, there is some, well, I mean, so maybe the same, maybe representations which lead to those deformed systems can be deformed. And
but the issue of parameters, yeah, that was one of the reasons why this paper is still in preparation. Each time I think, oh well, is there a way to insert here parameters like in the cycloatomic daha, and I didn't manage, and then the longer the longer it takes, then you don't want to to embarrass yourself by missing that, and then the longer it takes, the more embarrassed you feel not to
But Reigns should have somehow the most general parameters. So doesn't he?
He says that he cannot get more parameters in this case. No.
Okay, so probably, I mean, he has some algebraic geometric approach. So most likely, if he cannot get them, then there are no.
Right.
So those parameters in cyclotomic case are the Kähler parameters of the cyclic quiver, or the T1 through Dn.
Yeah.
So which ones are Kähler, which are not? Yeah. Okay. So there is a.
Like
I mean, in one realization they are Kähler, and the other realization they are.
Yeah, yeah, but like on the mirror side, you know, in this 3D mirrors, you have a different quiver. You have A0 star with a framing end, right?
With multiple errors.
Yeah,
right?
with multiple. That's right. But like, yeah, so there are two versions.
So for the quiver, cyclic quiver of length L, those parameters correspond to the value of the group valued moment map.
Yeah. Okay. And then in Oleg, in your story, you turn them off, right? So you would send them to 0.
Well, they were present, but only combination of them was relevant. Yes. So in a way, it's a limit. It corresponds to taking limit them going to infinity, I think, if I remember correctly.
And the parameter which was relevant was the cyclic product, right? Like the order product T1, T2.
Yes.
Yeah. I think we have. Great.
So another question. So Oleg, I think we had a correspondence with David Gaiota, where he, in their paper, what arose is some deformed systems which are more general than the ones you considered, with 3 groups of variables.
Yes.
And so do you understand? Do you expect them to extend to these Q settings and deformed settings?
Yes. Well, it's yes, we're doing some work with Martin Halnisch just to construct them kind of explicitly.
Okay, so you're working on this.
Yes.
Okay.
But this should be probably off the record. Right.
May I ask you, Oleg?
Yes.
So my question is very stupid, naive. So is there any connection with Skriani algebra or some kind of integrable lattice model setting? No, originally Shibuka Ueno tried to kind of understand the 8-vertex model or Skriani algebra, things like that. You start from such.
Yes, I know that for these guys, for instance.
Yeah. So if you truncate this operator acting on some certain space, you get.
I know that. Yes, the was it Felder and Pasquier?
Yeah.
They recovered Bajanovs.
Yeah.
Sorry, Vilavens.
No.
Vilavens are made.
Anyway. So Skriani algebra is something you can create from such by very complicated way, introducing higher spin analog of such probably. No, so I'm just very naive. I'm asking you if you can find some connection with such story.
No, I cannot tell you. Right. Okay. Maybe I should stop.
Okay.
Yeah, thank you much, Oleg. Yeah, it was a lot of interesting ideas which we can all think about and follow up on. Great. So our next speaker is here, Matt. Right. So are you ready? Can you try to share your screen?
Yes. Hello.
Yeah, we can see the slides. Yeah. So
See the slides.
yeah, I think we can just move on. Yeah. So are you ready?
I'm ready.
Great. So our second speaker is Matthew Bullimore from Durham, and he will speak about 3D supersymmetric theories on an elliptic curve.
Okay. Hi, everybody. Hello to some old friends, and nice to meet you if I haven't met you before. So I'd like to tell you about some work with Daniel Zhang. He's a PhD student in Cambridge. And I should say straight off the bat that I'm not necessarily an expert in integrability or integrable systems. My background is mostly in field theory and supersymmetric field theory, but from time to time, as I'm sure many of you know, these subjects overlap in a very beautiful and interesting way. And this is one of the things that I'd like to talk about today. So the talk is about some three-dimensional quantum field theories, supersymmetric quantum field theories, and studying these theories on an elliptic curve and associated structures that go together with that. Okay, so yeah, let me also say that it's going to be about mainly from a paper that's already come out and some work in progress, but also there was a paper around the same time, on the same day, of Dedyshenko and Nekrasov, which takes a slightly different perspective. You might be interested in as well. Okay, so let me just give an introduction first and tell you what I'd like to talk about. So let me just go back to 1982. And so we learned from Witten that, that by studying supersymmetric quantum mechanics, we can learn about Durham cohomology and Morse theory and topics like this. So in particular, if you study a quantum mechanics, a supersymmetric quantum mechanics with some target space, it's a sigma model. And I'll always call the target of my sigma model X today. And X should be, well, it will carry in general some geometric structure. But this old result says that if you study the ground states of this quantum mechanics, so in general, there's a Hamiltonian, it has a spectrum. But if you study the ground states of this quantum mechanics, these are the supersymmetric ground states, then they can be put in one-to-one correspondence under some assumptions with classes in the Durham cohomology of the target space. And this is really Durham cohomology realized using Hodge theory in this case. So there's a connection between the states of quantum mechanics and Durham cohomology. And there are expected to be generalizations of this result as you start to go to field theories in higher dimensions. So if you go up to 2 dimensions, the expectation is you go up to K theory, and to 3 dimensions on an elliptic curve, then you go up to studying what might be called elliptic cohomology. And so I think there have been various ways to think about this. But one of my plans, so one of the ideas was to make this connection much more precise. And I should say straight off the bat that this story, and in particular, generalizing this story to higher dimensions on a circle or on a torus, is much more interesting and intricate and rich when there are symmetries in the game. So we don't just consider any target space X, but the target space has some isometries, a symmetry group that are, and it's much richer in that case. So what am I going to do today? I'm going to tell you about a particular class of 3-dimensional quantum field theories, and we're going to study them on an elliptic curve, E, which depends on some complex structure parameter tau. And so what I mean by that is we'll study the system on, really it's 3-dimensional. We'll study the system on the product of a real line times the elliptic curve. And it's interesting whenever you do that, if you have this symmetry group around that are called T, then you can always introduce, well, flat connections for this symmetry group on the torus. And the type of problem I'd like to consider is the kind of analog of this old problem here, supersymmetric quantum mechanics. You want to think about this three-dimensional system as a quantum mechanics living on the line, and ask about the spectrum of its Hamiltonian, and in particular, what is the spectrum of supersymmetric ground states? And moreover, perhaps, how do those supersymmetric ground states depend on various choices you have, like this choice of background flat connection on the torus? And the idea is that by studying this system and by studying the ground states, we tried to give a model of this thing called elliptic cohomology. Okay, so what does that involve? So the idea, yes, is to study the ground states of this system, and in particular, how they depend on the flat connection. Oops. So in physics, that means we study what's called the Berry connection for the space of ground states. There's a connection on the vector space of ground states as you vary these parameters. And supersymmetry gives you a very direct relation to the study of what are called doubly periodic monopoles, or perhaps some generalizations of doubly periodic monopoles. And what seems to be happening is that the study of these doubly periodic monopoles, thought of as the Berry connections for this quantum mechanics, is providing some bridge or connection between, on the one hand, this elliptic cohomology theory, and on the other hand, quantum K theory, which is quite a different thing. Although in some sense, these are both different types of lifts of K theory. But this, I guess this is an elliptic workshop, so I'm going to talk about the elliptic side of this thing today. And indeed, many of the one of the motivations for doing this was
Matt, are you saying they're on equal footing in some sense, or sort of one is above the other, right? So I'm not sure I understood.
Yeah, I'm not sure that I want to make a very precise statement, because I don't know what it is the honest answer. But what I'd like to argue is that the structure of this full Berry connection in this case encodes both the elliptic cohomology, equivariant elliptic cohomology, and the equivariant quantum K theory of the target space of
interesting. Okay.
So let me just leave it at that. Yeah, thanks. So one of the motivations is to connect to to various topics in enumerative geometry, representation theory, and integrability, and in particular this work of Eigen, and Kunkov on elliptic stable envelopes and elliptic R matrices. And the idea, or one of the motivations, was to give a very precise physics realization of those constructions. And that's something that I think we were able to do. Okay, so that was my introduction. So I'll just pause here. If there are any questions, please go ahead. Yeah, okay. Yeah, please do feel free to stop me. I'm very happy to stop and explain things in a different way, or if that's helpful. All right, so let me just give some background then about the type of theories that I want to study and how they're related to mathematics. And this section is essentially going to be formulating various aspects of group actions on Kähler manifolds in physics language. So I want to consider three-dimensional quantum field theories with at least n equals to 2 supersymmetry. That's 4 supercharges. And the type of geometry this is related to is Kähler geometry. So in particular, you can think of a class of models which are just sigma models, whose target space is some smooth Kähler manifold X. and that will be my main example today. I'll largely think about it as a sigma model, but often in physics, we work also with gauge theory. And you could also imagine that you're studying a gauge theory in some regime, or some geometric regime where you flow to a sigma model onto this target space X, which might be the Higgs branch of the theory. And in my talk today, I'm going to assume that the target space is compact. Sorry about that. That's not a restriction. It's just an assumption today to remove some details and give the simplest possible examples. Okay, so as I said in the introduction, this is an important point here will be to study symmetries. You want to study quantum field theories that have a global symmetry. And so here I'll assume that the theory has an abelian symmetry T. So T is a torus. And the fact that it's a symmetry of the quantum field theory means that it will act by isometries of X, preserving the Kähler structure. So it'll act by Hamiltonian isometries of X. And one assumption that I want to make is that the T acts on X with only isolated fixed points, which I'll call P, and I'll label by some index alpha, running from 1 to n. So my trivial example will be that I'll keep coming back to in the talk is just taking X to be CP1 with a standard U1 action that rotates CP1, preserving two fixed points, P1 and P2, it's like the North or South Pole. I guess the Earth is turned on its side here. Okay, so this is the kind of problem that I'm looking at. Maybe I'll just say for those of you that know about these things that I'm going to assume a bit more than this. I'll assume that this T action is GKM. That's not going to be too important, but I think it's an assumption for what I want to say. All right. So there's a sigma model whose target space is X, and it has a symmetry T. And associated to this symmetry, we can turn on various parameters in the theory. And so in particular, one thing you can do physically is to turn on real masses, mass parameters. And these are valued in the Lie algebra of that symmetry. And the way this works, physically, what's roughly happening is you've got your sigma model, and then you're putting a potential on top of the system. And the potential is kind of localized. It has minima at the fixed points of this T action. And that's what a mass parameter introduces in a sigma model. One way to think about that is geometrically in terms of a moment map. So it corresponds to introducing what you might call a real superpotential that I call H. And that superpotential is just the moment map for the action of the one parameter subgroup of the group T that's generated by this mass parameter M. And then by a standard argument, standard theorem, if the masses are generic, if this is a generic value of a generic element of the Lie algebra, then the critical points of this superpotential will be the same as the fixed points of the T action. And in physics, what's happening here is that we start out with a sigma model, and then once we introduce the mass parameters, the system becomes completely massive. There are just a finite number of isolated massive vacua in the system. And you can think about the critical points as those massive vacua. Okay. So we have these massive vacua. There's a bunch of isolated vacua. But we can also have domain walls that interpolate between those vacua. So the picture looks something like this. You have a vacuum alpha on the left, some vacuum beta on the right. And then there's a domain wall that interpolates between the two. And you can think about these domain walls as also geometrically in terms of this moment map, this function h. In particular, they're gradient flows for the function h. So you imagine each domain wall corresponds to a gradient flow that starts at alpha and ends at beta. And the tension of that domain wall is controlled by exactly the difference between the values of the superpotential at those points. Okay. So it's very useful in this business to, well, let me say the following thing. So I mentioned here that the critical points of H for generic values of the masses were the same as the fixed points of the T action. So I just want to make a bit more precise what it means for a mass parameter to be generic. And what are the loci where that's no longer true? What are the special values of the masses where that's no longer the case? And one way to formulate that is in terms of these domain walls. Because you could imagine a situation where you have, for generic values of the masses, all of the vacua are completely isolated, and the domain walls have some tension. But if you go to a special locus in the mass parameters where there's some domain wall between two vacua whose tension goes to 0, then that means that those vacua are no longer really isolated anymore. They can be connected, and a moduli space opens up that's connecting the two. So domain walls is a very useful way to encode that idea. And so in particular, you want to look at hyperplanes in the space of mass parameters, where the tension of domain walls goes to 0. And that means that these vacua are no longer isolated anymore. And you get an extended moduli space opening up that connects that pair of vacua. So I'll give an example. This is a bit abstract, I think, but I'll give an example in a second. But the general picture is the following. You have your space of mass parameters. It's just an affine space, if you like, R to whatever the rank of the symmetry group is. And then there are all of these hyperplanes that pass through the origin. And these are loci where these are kind of non-generic loci in the space of masses where the vacua are no longer isolated and there are tensionless domain walls going between them. And one way to think about, or one way to label or think about these hyperplanes is to label them by weights of T. And the way that works is that the tension of the domain wall is proportional to the inner product between the weight and the mass parameter. So it's proportional to the mass. Okay, so roughly what's happening here is if the mass is kind of orthogonal to the weight, then the tension of the domain wall goes to 0. And there's a way to think about that weight geometrically in terms of the target space, is that it's kind of a common weight of the tangent, a common T weight of the tangent spaces at these two, at the various fixed points. All right, let me just give an example. So hopefully if that was probably too abstract, but here's an example. So consider P1 with the symmetry rotating the two sphere with two fixed points, P1 and P2. So there are two massive vacua, P1 and P2. But there can be domain walls that interpolate between those vacua. And the tension of those domain walls is proportional to the mass that you turn on. There's a single mass parameter here because there's a single U1 symmetry. And the constant of proportionality is basically the Kähler parameter, the size of the P1. But you see very clearly that here, if the mass goes to, for non-vanishing values of the mass, then there are going to be, the vacua are completely isolated. Another way to say that is the critical points of H consist of just the 2 points, P1 and P2. But then at the origin where the mass is 0, then the tension here, this domain wall goes to 0. There are domain walls that kind of interpolate from P1 to P2. and a moduli space opens up. And of course, in this case, you're just going back to the sigma model in the absence of mass. And the moduli space that opens up is a copy of P1, is the whole P1. Okay, so this is the kind of thing that's happening locally when you go to a hyperplane. You have a pair of vacua, and a P1 moduli space is kind of opening up when you go to this locus. Okay, so that was a quick summary of some of group actions on Kähler manifolds and how to think about them in terms of physics. So maybe I'll pause here again and see if there are some questions.
So away from those hyperplanes, you have massive vacua, and then as you go either to the boundary, like, or on the corner, like the even bigger modular space opens up, right? Yeah.
That's right. Yeah, that's right. And so the more intersections you go to, the bigger the moduli space that opens up. So, in this picture, somewhere generic, you might have 3 isolated vacua, and on each of these hyperplanes, that's where a P1 opens up, connecting a pair of vacua. And then if you go all the way to the origin, it becomes a whole P2.
Right. So will this be related directly to this Okounkov-Smirnov picture, right? With the, the reflections and what is it? Basically, this Alkovs is the same stuff that they're talking about, right?
Yeah, I'm not sure exactly what.
Never mind.
That's my lack of knowledge. But
I can wait. Yeah.
Yeah. Sorry. I expect so, but I'm not sure exactly what that is. But yeah, I think this type of structure appears in a lot of places. Yeah. All right. Thanks. So let me then get to what I actually want to talk about, which is studying this class of theories on an elliptic curve and studying their ground states. Okay, so this is the setup. I want to put this 3-dimensional theory on a real line times some elliptic curve with some complex structure modular parameter tau. And I want to preserve the most amount of supersymmetry that I can, namely all of the supercharges. And so to do that, I choose Ramon-Ramon boundary conditions for the fermions. So this is a choice of boundary conditions where I can preserve essentially all of the supersymmetry. That means 4 supercharges. And so if I think about kind of reducing the theory on the torus to get to quantum mechanics on the real line, the quantum mechanics will have 4 supercharges. Okay. And so what I'm really going to be interested in doing is thinking about this system as a quantum mechanics and asking what are the ground states of the system. But there's another thing we can do. So I've already in the first part turned on these real mass parameters that were associated to the symmetry T. So we've already introduced those. They're valued in the Lie algebra of the symmetry T. But now we're on a torus and we have some topology. And so we can do something else in a way that's consistent with supersymmetry. We can introduce a fixed choice of background flat connection on the curve. And so I'm going to call that flat connection A rather loosely. Although what I really mean by that is the holonomy around, it's a combination of the holonomies around the 2 cycles of the curve. And under large gauge transformations, that shifts by some weights here. And so the flat connection, the space of flat connections is also itself a torus. And in particular, the space of flat connections is going to be a rank T dimensional torus. And you can basically identify it with rank D copies of the underlying curve. So alongside the masses, we've now got 2 sets of parameters. We've got the masses, and we've also got the complex flat connection, the flat connections. And those two parameters combine so that the total parameter space, you take R times the elliptic curve, and then you take rank T copies. So the R is the masses, the E is the complex flat connections. And it's going to be important here that this is a multiple of 3. That's kind of important. One way to see that should be so is that there are 3 scalars in the vector multiplet of an n equals to 4 quantum mechanics. And these are expectation values for those scalars. And that particular feature will also control the structure of the Berry connection, which I'll come to. Okay. So what I'm interested in now is studying, so I've got these background parameters in the theory that I can turn on, and I'm interested in studying the spectrum of ground states, the supersymmetric ground states of this problem. So these are states that are annihilated by the Hamiltonian, or equivalently, they're annihilated by all of the supercharges in the quantum mechanics. And the general expectation is that provided you turn on generic values of these parameters, of the masses and the flat connections, you'll have the same number n of supersymmetric ground states as I did fixed points on the target space X. So I'm not going to go into too much detail about why that is, but I'll take that as a fact. So in particular, you expect to find ground states that are in some sense in one-to-one correspondence with fixed points, or if you like, isolated massive vacua of the theory in flat space. So I'll label them by psi alpha, where alpha runs from 1 to n. This is very vague. In general, it's very difficult to explicitly construct wave functions for these states in the presence of all these parameters. But one thing we can do, or one thing we can learn, based just on supersymmetry, is to study how these ground states depend on the background parameters in the theory, on the masses and the flat connections. And that's something that's controlled by a Berry connection. So that's the basic idea. How do the ground states depend on the mass parameters and the flat connection? Well, okay, the Berry connection, if there are n ground states for generic values of all these parameters, we should expect the Berry connection to be a connection on a rank n vector bundle. That's what you would expect generically. But supersymmetry gives you a lot of extra structure. It gives that Berry connection a lot of extra structure. And that was studied in a beautiful paper of Chakotay, Gaiotto, and Baffa from 2013. And in this case, if you have a quantum mechanics with 4 supercharges of the type that we're studying, and you turn on these parameters, which are kind of, they're obtained by giving expectation values to scalars and vector multiplets, then the Berry connection has the following structure. It has a number of pieces. It has a connection on a principal SUN bundle, P. So it's rank n because there are n ground states. This is your kind of bare Berry connection, if you like. But it also comes with a bit more structure. There's in particular, there's a scalar field phi, which is a section of the adjoint of the bundle in the associated bundle in the adjoint representation. But that's also valued in T star, the dual of the Lie algebra of T. And putting those things together, we've got a connection and a scalar or a Higgs field. And together they solve a system of generalized monopole or Bogomolny equations on this background. And so these equations are really a big generalization of the doubly periodic monopoles. It's doubly periodic here because I have the elliptic curve, and it's a generalization because for ordinary monopoles we'd just be in 3 dimensions. Here we have to raise it to rank T. That's why we have a T star valued section here. It's related to that. Okay. in particular, if you just restrict to the case where T has rank 1, it's just a U1, then these will just become literally the Bogomolny equations for monopoles, and that's it. All right, so this is something that you know just from supersymmetry. So even if it's very difficult to write down explicitly the supersymmetric ground states as functions of all of these background parameters, you can still try to study this this Berry connection and study things like its asymptotic data and where the singularities or where the centers of the monopoles ought to be. And that gives you a lot of handle on thinking about this problem. So let me give an example, which is my example throughout CP1. CP1, we had a rank 1. The symmetry was just U1. It was rank 1, so we should just expect a regular monopole. There are two supersymmetric ground states, the north and the south pole of P1, and the target space is compact here, so it's just going to be an SU2 monopole. And it's the first, in this case, it's the first thing that you would write down. It's a single smooth SU2 monopole on R times T2. So these types of doubly periodic monopoles and the types of asymptotic data that you get was studied in some papers of Ward and Cherkis and Ward. And the picture looks something like this. You've got a base, which is parameterizing the mass. That's the thing from before. So the base here is like the hyperplane arrangement that I wrote before. But then above each of those points on the hyperplane arrangement, you've got a torus. And for generic values of the mass, nothing interesting is happening. But when the mass is 0, there's a kind of a monopole, a smooth non-abelian monopole situated at a point on the torus, which is kind of the 0 flat connection. Okay. So let me try to give a kind of cartoon of what the general type of picture looks like. So in general, we have to work on this R times the elliptic curve raised to some power, the rank of the symmetry. And the way I like to think about this is by projecting down onto the R factor. And so if you project down onto the R factor, you will recover this kind of hyperplane arrangement that I talked about in the first half. That's the thing. The base here is just the space of mass parameters, R to the rank T. And the picture is that you have kind of smooth monopoles. So monopoles are always codimension 3 loci. And so you have smooth monopoles that that sit above each of these hyperplanes in the base. So here you might, in this picture, you might be at a generic point. Nothing interesting is happening. But then you move on to one of the hyperplanes. And then you have a codimension 3 smooth monopole that sits at a point on one of the torus and fills the other torus. Something like this. And then you might move to another hyperplane and it's the opposite. And then if you move to the origin, all hell breaks loose. No, I mean, you can get higher codimension things happening. So to be a bit more specific, remember I tried to label these hyperplanes by weights in this way. Well, then the center of the monopole is given by a similar equation involving the flat connection. Let me mention a couple more things. Here I've only got kind of smooth monopole solutions. If it can happen if your target space X is non-compact, then you can also have singularities, singular monopoles, 't Hooft monopoles. And that's arising because if it might happen if your target space is not compact, it might happen at some particular locus that a non-compact moduli space opens up. The spectrum of your quantum mechanics is no longer gapped, and then you should expect a singularity in the Berry connection. Another feature is that you have control, even if you don't know what the solution is, you have complete control over the asymptotics. And the asymptotics are governed by the certain quantities called the effective Chern-Simons levels for the flavor symmetries in each of these massive vacua. So roughly you have control about the asymptotics, and you have control about where the centers of these smooth monopoles ought to be. Okay, are there any questions about this? Or? All right. So in studying moduli spaces of monopoles, it's often very useful to pass to some kind of spectral construction involving a spectral curve. And in the case of doubly periodic monopoles, there are many ways to do that. And so what I want to give you is just one particular way to build a type of spectral curve associated to this. It's a kind of algebraic data associated to the monopole. And that spectral curve is going to be the key thing that gives a connection to various types of cohomology theories. So let me just tell you what this thing looks like. So we consider a kind of spectral curve. And so I call the spectral curve S. And the way to think about it is that it's an n-sheeted cover of the space of background flat connections here. So the cartoon looks something like this. The base is the space of flat connections. And above a generic point, there are just n sheets, n copies of this space. But then whenever you have a smooth monopole, whenever you have a monopole center, labeled by these weights, lambda. So this is roughly this point here, for example. Then you have to glue the corresponding sheets together. So in a bit more detail, you can think about each of the sheets as each sheet is associated to a single vacuum labeled by alpha from 1 to n. And then if lambda is the weight where corresponding to a domain wall that connects a pair of vacua, alpha and beta, then at that point, you should identify those sheets, the two corresponding sheets. So indeed, sheets intersect at particular loci that correspond to the centers of the smooth monopoles. And in particular, if you identify a pair of sheets at the locus where the corresponding domain wall between the two vacua associated to those sheets become tensionless, and a moduli space opens up. So this kind of gives a type of spectral curve, which is like an n-sheeted cover. So let me just give an example of what this kind of thing looks like in this example. when the target space is just CP1. In this case, we said the Berry connection was a smooth SU2 monopole on R times T2, just a smooth SU2 doubly periodic monopole. And in this case, the kind of spectral curve that I'm talking about is just a two-sheeted cover. There are two copies of the curve, and they're basically just identified at the origin. Not the origin, they're identified at the distinguished point. This is roughly the zero flat connection. That's the case where the domain walls interpolating between the two vacua become massless and a moduli space opens up. So you see that the intuition is here that away from this point, the two vacua are kind of isolated and massive. They don't talk to each other. So the sheets are separate. But then if you go to this point, there are tensionless domain walls that connect the two. Everything mixes up and you have to identify the sheets. Okay. So that's the kind of cartoon of this thing. Sometimes it's useful to think about it slightly non-rigorously as solutions to some equations involving theta functions of this type. That's another way to think about this thing. Okay. So this spectral curve plays a very crucial role in equivariant elliptic cohomology. In particular, it's kind of the basic construction, and this goes back to papers in the 90s of Gronowski and Ginsberg, Kapranov. In particular, this curve S is what's called the T-equivariant elliptic cohomology variety of X. And so it, yeah, I haven't really told you what that is, apart from the thing that I said that it was. But the basic idea is that an elliptic cohomology class is essentially the same thing as a line bundle on this variety S. So if you and there's a one-to-one correspondence between those things. So to give an elliptic cohomology class of some target space X is the same thing as giving a line bundle, on this space S. And so then there's a basic question, which is, how do we construct those classes? How do we build line bundles on this space S from physics by some physical construction involving these three-dimensional theories? And so that's what I'd like to talk about in the final part of the talk. But yeah, maybe this is a good point again, just to stop and see if there are any questions. All right.
Equivariant is it equivariant elliptic cohomology or not yet?
Sorry, Peter, could you repeat that?
The equivariant is elliptic cohomology class. Is it equivariant or not yet?
Yeah, equivariant. So yeah, equivariant is really important here.
Yeah, good.
Yeah. Yeah, in particular T equivariant, where T is this this symmetry, that I've been, yeah. Okay. Yeah, that should have also been in the second line here. Thanks. All right. Okay, so what I'd like to say in the last part is that one way to build explicitly these line bundles on this this curve, this variety S, is to study boundary conditions for the three-dimensional quantum field theory. So let me explain how that works. So we want to study boundary conditions. And we're in a supersymmetric theory, so we want to consider boundary conditions that are supersymmetric, preserve some subset. There are various choices of different types of supersymmetry that you can preserve, but the type that I'd like to talk about is boundaries that preserve at least n equals to 2, 2,0 supersymmetry in 2 dimensions. So these types of boundary conditions have been kind of widely studied. These are some papers where they're studied, and they're very easy to construct. For example, in gauge theories, there are very explicit constructions that allow you to build boundary conditions of this type by, for example, starting with regular things like Neumann or Dirichlet for fields, and then adding extra multiplets, adding extra degrees of freedom on the boundary, coupled with superpotentials and things like that. So there are lots of tools and methods to construct and study boundary conditions of this type. So yes, so we were doing T-equivariant cohomology. So we'd like to study boundary conditions that preserve the flavor symmetry T. Could be that the bulk has a global symmetry T, but the boundary breaks it. We want to make sure that it's preserved. That's a restriction on the class of boundary conditions we consider. If we do that, it may be that there are still boundary 't Hooft anomalies for the symmetry T. And that's really important here because I want to start wrapping the boundary conditions on an elliptic curve and introducing background fields, flat connections. And so as soon as you start doing that, 't Hooft anomalies are going to be very important for studying the system. Okay. And so the basic idea, the basic observable that we want to study with these boundary conditions is to study the boundary amplitudes. So this is very similar to a kind of TT star type story. Now, so what is a boundary amplitude? Well, the idea now is that we study the system on not r times the curve, the elliptic curve, but a half line times the elliptic curve, where we place the boundary condition at the origin. So we cut off the space and put a boundary condition. And then we demand that as we go off to infinity in the other direction, that we demand that the system sits in this massive, isolated massive vacuum alpha. And then we compute the partition function, the supersymmetric partition function of that system. And we call that the boundary amplitude. And I write it slightly schematically as an overlap of states. Roughly, you can think about the boundary condition as creating a state in the quantum mechanics, and then you're taking the overlap with the supersymmetric ground states. But it's computed by just computing the partition function of this system. And that partition function behaves very much like a 2D elliptic genus. In particular, okay, it goes off to infinity, but you can imagine squishing the system down and reducing on the half line to get a two-dimensional system, and then you're computing the elliptic genus of that system. And so just like there are many useful ways to compute elliptic genera of supersymmetric gauge theories, likewise, for these kind of computations, you can compute, you can compute these kind of partition functions very explicitly using localization. So these are useful objects, and they're readily computable in examples. And the result will depend ultimately on the background connections that you turn on these A's. And in particular, one beautiful feature they have is that they end up transforming as their dependence on A is such that they transform as sections of line bundles on the space of background flat connections. So they're not invariant under, another way to say that is that they're not invariant under shifting A by large gauge transformations, but they pick up phases that mean that they transform as sections of line bundles. And those phases, or the quasi-periodicities that determine the line bundles, are basically fixed by the boundary 't Hooft anomalies associated to the boundary condition. Or really, it's the effective Chern-Simons terms in these vacua via anomaly inflow and the boundary 't Hooft anomalies associated to these boundary conditions B. So their quasi-periodicities are completely fixed by these things. And using that data, using how they transform under large gauge transformations, you can show that those amplitudes, each of which, as alpha runs from 1 to n, transforms as a section of a line bundle over the space of flat connections. Their quasi-periodicities are such that they glue to a single section of a line bundle on this spectral curve. So remember, the spectral curve was like an n-sheeted cover. So roughly giving a line bundle on the spectral curve is the same as giving n line bundles on the base, but you have to ensure that they agree at these points where the sheets overlap. And that's guaranteed by the structure, or what you can show is that that's guaranteed by the structure of these boundary 't Hooft anomalies. So in other words, these boundary amplitudes that you compute gives you a line bundle on this variety S, or in other words, it gives you an elliptic cohomology class. So there's a map here. We can take a boundary condition that preserves the symmetry T, and we'll get a T equivariant elliptic homology class. And that kind of generalizes the picture that you would perhaps have going back to ordinary supersymmetric quantum mechanics. One way to build a state, a cohomology class, is to give a boundary condition and evolve it. This is kind of the analog of that picture in this setting. Okay. Let me just check how the time is going. Okay.
Yeah, like 12 minutes. Yeah.
Okay, good. Yeah, let me just give an example then. So just to show you that this is something that's like explicit and computable. In this example, you take the target space to be P1. I'd like to explain how to build the classes, the equivariant elliptic homology classes associated to the 2 points P1 and P2. So one nice way to think about this model is to build it using a gauge theory. And the way you do that is you take an abelian gauge theory with gauge group U1, and then there are 2 chiral multiplets, phi1 and phi2 of charge 1. And we can build basic boundary conditions that involve basically a Neumann boundary condition for the vector multiplet. And you consider 2 boundary conditions B1 and B2, where you couple to certain extra degree of freedom called a Fermi multiplet on the boundary with a certain superpotential. And what that really does is it sets the coordinates phi1 and phi2 to 0 at the boundary. And they, of course, correspond to these 2 points, P1 and P2. And indeed, if you flow from the gauge theory in a regime, if you're in a regime where the gauge theory flows to a sigma model onto P1, then these boundary conditions will flow to Dirichlet boundary conditions, where the map in the sigma model is forced to land in P1, the points P1 and P2. So these are basic Dirichlet boundary conditions, basically, in the sigma model. And you can compute these boundary amplitudes very explicitly. It's basically given by the elliptic genus of this Fermi multiplet that you have to add here to impose that phi1 or phi2 vanishes. And that can be written in a simple way like this as a theta function. And then the boundary amplitudes are basically found by just evaluating this thing at certain points. So this is something very explicit that you can write down, and they glue to line bundles. They glue to sections of line bundles on this curve S, and they correspond to the classes of the 2 points P1 and P2. Okay. Okay, so that's basically what I wanted to say. Let me in the final 2 slides just give a hint about some of the things we did with this. So we had a special interest, of course, in theories where we had more supersymmetry, n equals to 4. This is the case where the target space X is hyperkähler. And in fact, we restrict the cases where X is a hyperkähler cone or a resolution of a hyperkähler cone. And these have all sorts of applications in representation theory and enumerative geometry. And there are many interesting classes of boundary conditions that you can build that are kind of in one-to-one correspondence with these vacua. So you pick a vacuum, you get a type of boundary condition, which we studied in a paper here. And so the thing that we did with Dan was, or a couple of things we did is we built explicit UV boundary conditions which reproduced certain classes of these boundary conditions. So in particular, the classes of what are called attracting sets of the fixed points and also the stable envelopes associated to fixed points. And so this in particular gave very explicit UV definitions of boundary conditions whose boundary amplitudes reproduce the elliptic stable envelopes introduced by Eigen and Konkov. That was at least for abelian theories, actually. And we also studied mirror symmetry. It turns out that the boundary conditions associated to these two things are exchanged under mirror symmetry. Okay. Finally, one other thing we studied was well, so far in my talk, I assumed that the mass parameter, this m, was basically a constant that you can turn on. It was just a number. But it's also interesting and compatible with supersymmetry, the supersymmetry that was relevant for the talk, to introduce a position dependence. So you can imagine that this mass varies in space. So particularly, you can kind of consider a situation where along the real line R, the mass depends on position and kind of interpolates between two chambers of this hyperplane arrangement. So that, the kind of picture at the beginning, like this, you can imagine you're moving from one chamber to another in real time in space when you do this. This is the type of thing that's called a Janus interface in physics. And what we showed is that by studying the correlation functions or the overlaps of these types of Janus interfaces, we were able to build elliptic R matrices that were constructed, and their construction in terms of stable envelope, elliptic stable envelopes in Eigen-Eigenfunctions. One nice feature, let me just say, one nice feature of this picture is that Yang-Baxter is in some sense manifest. It follows from the fact that none of these computations depend very much or at all on the profile for this mass. It can wiggle however you like, as long as it starts and ends in the same point, that's okay. And by varying how this profile looks, you can kind of interpolate between the two sides of Yang-Baxter, for example. Okay, so I think that's everything that I wanted to say. So I'll end there.
Thank you, Matt, very much for the nice and clear talk. Questions?
I just have a general question.
Yeah.
So in the 3D n equals 4 theory, there's a beta gauge correspondence that these theories are connected to XXZ spin chains. How should I think of this correspondence in this kind of picture? Or is it not related at all?
Yeah, the connection to XXZ is the thing that I didn't talk about. It more goes along the lines of the thing that I didn't talk about, which was the
second part of the K theory.
The second part here, the equivariant quantum K theory. So, I mean, maybe I'll say something very quickly about that. So there's another type of spectral curve that you can build for these doubly periodic monopoles, where you study the holonomy of the Berry connection around one of the cycles of the torus and use that to build a spectral curve.
But then do you need to unwrap the other cycle, or you can still keep it finite?
No, you can keep it finite. You can keep it as it is, and it's kind of important to do so. So that, yeah, you compute like the holonomy of the Berry connection around one of the cycles of the torus, and that will depend on the holonomy around the other torus, and the mass. And because the holonomy is periodic, that means that that's a periodic variable, and that's kind of important. And then you build something like a characteristic polynomial of that to get a spectral curve in the standard way. And the equations that define that spectral curve are basically the same equations that describe the equivariant quantum K theory or quasi-map K theory ring of the target space X. And those equations are basically the beta equations for the 3D n equals to 4 gauge theory.
Oh, nice. Yeah.
So I hope that kind of answers the question.
Thank you.
Is this fact in the paper or not?
Yeah, I mean, actually, I think this was, this connection was pretty much noticed already in the paper of Chalykh and Vafa. So that's how thank you. I should have pointed, as this conference is about integrability, I should have at least pointed that out. So yes. Thanks.
So since Mykola Didoshenko was unable to speak, can you maybe summarize the connection work? So what's different in their paper and how it connects to yourself?
Yeah, they were studying many of the same problems, and I think again, like the motivation was to give a kind of precise physical realization of these beautiful works of Eigen and Kunkov on elliptic stable envelopes and elliptic R matrices. And I think they took a slightly different approach, but largely obtained similar results. And they had a much nicer and more detailed description of these Janus interfaces that was really very nice. Yeah. But they, in some sense, well, I don't want to.
Yeah, so you can. So sorry, I interrupted you. Go ahead.
No, I was just, I don't want to paraphrase their work too much, but that's all.
Okay.
Yeah, go ahead.
As you're saying, then if the target is not compact, then you have singular monopoles and your analysis goes verbatim, right? So that's how you did it for hyperK for this story.
Yeah, that's right. And you get the singularities all over the place in the n=4 story. Yeah, that's right.
And then did you say that you did calculations in abelian, like
I think that the general story is broadly true, but the thing that we only really did in the abelian case was to build these explicit UV boundary conditions that reproduce the stable envelopes. That was something so far we could only do in the abelian case.
Right, because it sort of uses your results from this paper, right, with a Tudor dividend adjustment.
I mean, I think I know how to do it in the non-abelian case as well, but it's just technically, I think, a bit more involved.
Okay.
Yeah, but I think there's probably one area of distinction between with the paper of Mykola and Nikita, is we took a very much UV perspective where we kind of build a very explicit boundary condition in the UV, where I think they were taking a more kind of infrared sigma model perspective on the boundary conditions that reproduce the stable envelopes. So they were kind of nicely complementing in that sense.
And you see how they flow to each other, right? So,
yeah, they indeed. Yeah, that's the idea, is that these UV boundary conditions kind of flow to the things supported on the stable envelopes. Yeah.
Excellent. Very nice. Thank you. Other questions?
All right.
Oh, okay. Yeah. Thanks, Matt. Yeah. So just in time for the next talk. Shlomo, are you ready?
Yes. Try to share the screen.
Break and then begin.
Okay, do you see it? No?
Yeah, we can see it, yes. Yeah, and we see your annotation as well.
Okay, great.
Yeah, let's take a break, a couple of minutes, and then begin. What's it, 11:03? Are you now in Israel?
Yes.
Back home.
So you are in Berkeley, Peter? Or?
Yeah, I'm still in my backyard.
Oh, that's nice. And you were flying somewhere from somewhere.
Yeah, I was.
You are brave.
I gave a talk in Louisiana State University where Anton Seidel works. Yeah, so like somehow I, I used to, schedule things in advance. I didn't look at the calendar. I forgot that the same week I have a bunch of lectures and seminar talk. So I had to book a flight back at 6 a.m. so I can just make it to the evening session.
Shlomo, I'm sorry, I might have to leave a little bit.
Yeah, sure. Yes,
No,
it's all recorded and send me the slides. I'll put them on the website.
Thank you. I have to get home for bedtime.
Of course, yeah.
Yes. Yeah, these Zoom seminars are nice, but it's crazy with time. It's 9 p.m. for me, but it's not. We had seminars like in this QFT and geometry by people, for whom it was like midnight. That was.
Yeah, so that's why I think the best planning is to have a morning session, evening session, like US time, and that would translate to basically folks in Asia can attend one, and folks in Europe can attend. Well, depending on the sleep schedule, 1.5.
Yeah.
Well, it's only 7, but I guess it's kids' bedtime, so.
Yeah, sure.
Yes, so I'm after 3 coffees, so hopefully I'm okay. And I'm, refilling continuously. So.
Yeah, that's nice. Okay, maybe we should begin. You ready, Sergey? Yeah, good. So our next speaker is Shlomo Razamat from Technion, and he'll be talking about comments on modularity of the Schur index.
Okay. So thank you very much, Peter. So I would like first to thank Peter and Slava for organizing this very nice workshop. I think it's very important, especially in these times. And I learn a lot from these meetings featuring both more physics and more maths oriented people. So I will be talking about some comments on modularity of the Schur index. So Schur index is a very old subject, and I will try to present some little bit lowbrow computations, but I think they are interesting. And again, maybe I would very much want to get feedback from the more massive people, because it might be that we're rediscovering some very well-known structures, but at least the physics of these structures is not clear to us at all. So this is based on a paper we wrote with Chris Beam and the student of Chris, Palash Singh, a couple of months ago, and some work in progress. And I will also mention some work we did with Gabi Zafrir a couple of years ago, and with my undergrad student, Michael Loren Perelstein, which we never published, some collection of thoughts. And I also want to mention a very nice paper by Wolfgang Pillers and Iwan Pan, which appeared in the same day as our paper. It was coordinated, and it has a lot of very nice complementary results to ours, and I will mention them also. Okay, in a sense, this paper is much more mathematically rigorous, and our paper is much more experimental. So I will discuss that. So the outline of my talk will be as following. I will spend half of the talk roughly reviewing well-known results about indices and special functions and Schur indices in particular, to put everything in perspective. And then I will discuss our novel results about quasi-modularity of these Schur indices, in which sense the Schur indices enjoy this nice but not quite well understood quasi-modular properties. And then I will end with briefly with comments how this structure, this quasi-modular structure, should be generalized to mock modularity. So the talk will not be divided into 3 parts really. It will be a smooth kind of transition from one part to another, but ideologically, that is what I want to tell you about. And please stop me with questions anytime. So the framework of what we are doing is physics, supersymmetric physics in 4 dimensions. So we are trying to understand n = 1 supersymmetric quantum field theories in 4 dimensions. And luckily, for these theories, there is quite a big variety of things that we can compute exactly and non-perturbative. So there are certain partition functions that we can compute, and what is important about these partition functions is that they are invariant under changing various continuous parameters. For example, they are invariant under exactly marginal deformations, and thus computing them at weak coupling, we can probe strong coupling physics, and they're also are G invariant. So we can compute these quantities in the weakly coupled UV and learn something about the infrared physics. So one very useful and very concrete example of a partition function that I will discuss today is the supersymmetric index. And this is also the context where a lot of very standard hypergeometric elliptic in types of integrals, which are one of the main topics of this workshop, appear. So this index was defined by these people a long time ago, and also in the work of Rommelsberger. So the index is, in the end of the day, some function of a collection of parameters. To compute it, we need to trace over the Hilbert space of the theory in radial quantization with very particular weights. So we some over states or operators with a weight which is -1 to the power f, and then we turn on these parameters Q and P, which couple to some collections of charges. So implicitly in this index there is a supercharge, and these collections of charges commute with that particular supercharge. So J1 and J2 are SU2 are cartons of SU2 times SU2 isometry of a sphere, and the R is the R symmetry that our theory has. And in this talk, I will use always the superconformal R symmetry. Maybe at one point I will do something else, but I will always use the superconformal R symmetry. Very often, when computing these indices, it's very convenient to use some other choice of R symmetry, but for sake of simplicity in this talk, I will use the superconformal R symmetry. So these charges couple to these two parameters Q and P, which are always there for any n equal 1 SCFT, and one can turn on other parameters, which I denote here UI, which couple to the Cartan generator of some global symmetry that our theory might have. Okay. And the important thing about these indices is that they are very easily computed. So the basic idea is that if you are given a Lagrangian, an n equal 1 Lagrangian defined in terms of fields, in terms of some chiral superfields, some vector superfields, and your theory might also have some superpotential. What you do, you first compute the indices of all of the chiral superfields, and say you have a chiral superfield with R charge R. Here, then computing the index, you simply get the elliptic gamma function, where the R charge R is encoded in it in this power of P times Q, which appears in its argument. So here is my definition of the elliptic gamma function, which is a standard definition in this more physicsy literature. And this Z here is a fugacity for some U1 symmetry. Okay, so in all of the expressions that I will have, this elliptic gamma function implicitly depends on these parameters Q and P. I will not write these dependencies, these parameters explicitly, just to save space. Okay, and once you have all of this, contributions of all the chiral fields, you can write an index of some gauge theory. So here is some random example of SU3 n equal 1 SQCD with an F equals 6. So you write the contribution of all the fundamental fields and anti-fundamental fields. These are gamma functions written here. In this particular case, the R charge is 1/2, so that gives rise to this 1/4 power here. The contribution colored here in green is the contribution of the vector superfields. And then you perform this integration, which basically projects on gauge invariant states or operators. So this is a very simple and explicit computation that one can perform. So this connection to of these index computations to elliptic, these types of integrals was first observed in this paper by Dolan and Osborne, and first developed very extensively by Slava and Vartanov already many years ago. So one question that I will want to ask is whether these types of expressions have any interesting modular properties. Okay, this is a very vague question, and we will make it a little bit more concrete as we go on. So what do I mean by modular properties? So we can parameterize this P and Q in the following way with these parameters tau and sigma, and ask whether anything interesting happens when we take tau to -1 over tau and sigma to -1 over sigma. At the level of these contributions of the single chiral superfield, which are just elliptic gamma functions, there is this well-known result of Felder and Varchenko from many years ago, that these actually have some interesting transformation property with some cubic polynomial in this parameter zeta, which appears here. And Spiridonov and Vartanov, again, 10 years ago already noticed the connection of this polynomial to the anomaly polynomial of this theory, which here is just a free field, and it generalized to gauge theories. And an interesting question is whether one can understand this SL3Z property, or this what is the SL3Z property or the modular property of more complicated theories, not just gauge, not just free fields, but general gauge theories. And progress towards understanding that was done in a paper by Gadet. And a couple of years ago, I will not discuss this work in any detail here. I just want to mention. One thing about this object, this observation, is that SL3Z is a rather scary object to simple-minded physicists like me. And what we would like to do is simplify somehow the discussion. And to simplify the discussion, we will discuss a certain degeneration limit of the index, some simple limit of the index, where this SL3Z will become something more palatable to us, for example, an SL2Z. Okay, and such a simplified limit of the index exists, at least in the case when the theories we are discussing are n equal to supersymmetric. And we will generalize this point in a couple of slides. So if a theory is n equal to supersymmetric, one can take a very particular limit of the index by taking these two parameters to be correlated, taking p equals q to the half. And in this n equal to theories, there is usually an additional parameter t, which we will set to 1. This, if you are familiar with the Schur index technology and the standard notations in physics literature, that's not usually how you write the Schur limit. Usually it corresponds to q equals to t in the usual notation. So here I am using slightly different notation, and it has to do with the fact that I am insisting of taking some n equal 1 subalgebra in this n equal 2 subalgebra and taking the superconformal R charge here. Okay. So you can easily translate between the different notations, but I will stick to this notation. And the important thing is that the basic building block of this n equal to theories is what is called a hypermultiplet, which is just a pair of chiral superfields in conjugate representations under all the symmetries. And if you do this specialization, then these elliptic gamma functions degenerate to be just a very simple theta function. And the definition of the theta function that I will use is written here. So of course, theta function is much simpler object than the elliptic gamma function. In particular, if you want to study modular properties of anything, this object transforms nicely under SL2Z transformations, for example, as denoted here, where this P is now a quadratic polynomial. So, and again, that is the framework in which I will try to work. Instead of working with these most general indices, which are written in terms of elliptic gamma functions, we will try to understand the modular structure in this simpler setup of indices, which are written in terms of theta functions. And what we will try to understand, at least for a class of theories, whether there are any interesting modular properties that we can find. Okay, so here is some examples of indices, of Schur indices of some theories. So some of these n=2 theories have Lagrangians which are manifestly n=2 supersymmetric. For example of such a theory is an SUN SQCD with an f equals to n flavors. And for such theories where the Lagrangian is manifestly n=2 supersymmetric, we can just use this observation that the contribution of the hypermultiplet in this Schur limit degenerates to this theta function, and just take the technology that I presented before, and instead of elliptic gamma functions everywhere write corresponding theta functions, and the indices take this simple form. Okay. However, not all n=2 theories have n=2 Lagrangians. We know of some n=2 theories for which we only know n=1 Lagrangians, and these Lagrangians flow in the infrared to SCFTs where supersymmetry enhances. And here is an example of such a theory. So this is a famous theory of Minahan and Emeshansky, which has an E6 global symmetry. And in 2019, 2.5 years ago, I think Gabi Tzafrir found a Lagrangian for this theory, which is n=1 supersymmetric. And this is the index of that Lagrangian following the general rules of computing indices that we have discussed. And in particular, one can take the limit of p equals q⁻² in this Lagrangian and obtain the Schur limit of this object. The transformation, since the R charges here are different, not all of them are 2/3 are the free R charges as in the n=2 case. For example, this field has R charge 4/3, this field has an R charge 1/3. The translation is a little bit more complicated. You will not only get such theta functions, but more general objects. But in any sense, in any way, you can compute Schur indices from these Lagrangian expressions. A couple of months ago, Iñaki with friends found yet another Lagrangian, a completely different Lagrangian for the same theory, again with n=1 supersymmetry. So you can use those Lagrangians, and there are many other theories. For example, Argyres-Douglas theories for which we know n=1 Lagrangians, and we can compute Schur indices for them. So one thing that we will ask is whether such integral expressions for the index for various n=2 theories have an explicit evaluation formula. Can we explicitly evaluate these types of expressions using known functions? And later on, study modular properties of these types of objects. Of course, with elliptic hypergeometric types of integrals like this, we don't usually have explicit evaluation formulas except for some cases, but here we will see that for a large class of integrals, large class of cases, and which involve these two cases written here, we will be able to find evaluation formulas in terms of some nice modular objects. Okay. So before we continue, let me make a comment about an n=1 version of the Schur index. So I already mentioned that even if we have n=1 Lagrangians for n=2 theories, we can define these Schur indices. However, we can also go one step further and try to find some degeneration limit also for n=1 theories, which are not n=2 in any sense. So they are not n=2 in the UV, and they don't flow to n=2 theories in the infrared. So if two conditions are satisfied, that all the fields in the theory can be assigned the same R charge, and that R charge doesn't have to be the superconformal one, but if we can find an R charge R, which could be the same for all the fields in the theory, and the spectrum of the fields is not chiral, that means if we have some representation, also the conjugate representation exists in the theory, then taking a degeneration limit like that, p equals q to the power 1 minus r over r, again, all the elliptic gamma functions that appear in the definitions of the index degenerate to theta functions. And again, we have some much simpler object that we can study. We cannot do it for any theory, but there are large classes of theories for which this can be done. For example, if we have a non-chiral conformal gauge theory, which is only n equal 1 supersymmetric, we can assign R charge 2/3 to all the fields, and we can perform this degeneration and obtain these simple indices. So this is something I will mention again in the very last slide of this talk. So in the case of n equal 2 supersymmetry, the Schur index, the Schur limit of the index has a lot of physical motivation for it. For example, it is something which counts more supersymmetric objects. It's not clear what is the physics that simplifies the index computation here, but I just want to mention that the index does simplify for particular classes of n equal 1 theories. Another thing I want to remind is that I mentioned that there are these theories, n equal 2 theories, which have Lagrangians, and there are these n equal 2 theories which have n equal 2 Lagrangians, and theories which have only n equal 1 Lagrangians. But actually, there are many theories, or in some sense, most of n equal 2 theories we know about. We don't know of any Lagrangians that describe them directly. However, we can deduce existence of these theories by some geometric consideration. So the way it goes, we start from 6 dimensions with some 2,0 theory. We place the 2,0 theory on some compact space with some punctures, and then we flow into infrared far below the scale set by this Riemann surface and obtain an effective 4-dimensional theory. So in this way, we can define a lot of 4-dimensional theories with n equal 2 supersymmetry. These theories might or might not have an alternative description using Lagrangians directly in 4D. Some of them have, but most of them do not have such a description. But we're still interested in understanding their properties. And in particular, we can compute supersymmetric indices for these theories, which are obtained in this geometric construction, whether we have Lagrangians or we don't have Lagrangians, at least some limits of the index. And the Schur index is one of those limits. So first of all, on very generic grounds, you can show, you can prove that if you compute indices of these theories obtained in this compactification program, all of these indices are kernel functions of Ruijsenaars-Schneider operator. Okay, all this Ruijsenaars-Schneider operator, the algebra which defines it is the AD algebra with which we start in 6 dimensions. Okay? So all of these indices are kernel functions of these Ruijsenaars-Schneider operators. And then using this type of logic, these types of observation, again, using very simple derivation, one can obtain that the indices of theories which correspond to compactification on genus G surface with S types of punctures in the Schur limit have this very simple type of expressions for their indices. You can write them as sums of representation of the corresponding algebra from 6 dimensions. And then we have these quantum dimensions to this Euler character. And then for each puncture, we have a factor of a Schur polynomial here. And the fact that in this limit of the index, in the Schur limit of the index, Schur polynomials appear is the origin of the name of this limit of the index, calling it a Schur limit of the index. So these types of expressions we can obtain whether we have or we don't have an expression for the index in terms of a Lagrangian, and thus an expression for the index in terms of some hypergeometric elliptic integrals. So at least in the Schur limit, we always have these expressions. This can be generalized to a slightly less restrictive limit of the index, and where instead of these Schur polynomials, Macdonald polynomials appear. And one can wonder whether certainly suitably defined eigenfunctions of elliptic Ruijsenaars-Schneider model can be used to define some type of this TQFT like expressions for the index. one can formally make this assumption, but it is not clear if it can be made explicit or not. So it's an interesting open problem to discuss. Okay. And here are examples of such indices that one can write. For example, if one considers the SU2 NF equals 4 SQCD, which is a special case of the theory we discussed before, you can obtain this theory by compactifying an A1 2,0 theory on a 4-puncture sphere. So this theory happens to have the Lagrangian, this type of Lagrangian, and then one can compute explicitly the Schur index written here, and one can use the TQFT expression to write the index in this form. I write it here, this sign of proportionality, but actually we know explicitly what the proportionality factor is, and I will mention it later on. So we can explicitly write identities like that. And in the A1 case, we actually can prove these identities. These are not hard to prove. So we can show that these types of these types of integral involving theta functions give simple expressions using Schur polynomials. Here is the another expression that I mentioned, which is this E6 Minahan-Nemeshansky theory, where we can evaluate the index using a Lagrangian. Here, this is this Zafrir's Lagrangian, but you can use also the Lagrangian derived by Iñaki and friends. And this type of an expression should be given by this sum here. Again, this is the TQFT expression. Here, the theory corresponds to compactifying A2 type 2,0 theory on a 3-punctured sphere. And this, we don't have a proof of that, but I suspect that it is not hard to prove this type of an identity. Yet another example I want to mention, a much more complicated example here, a little bit more complicated maybe example. Here we have an A2 theory on a 4-puncture sphere, where 1 puncture is of one type and 3 punctures is of the other type. We have 2 different Lagrangians that were discovered by now. One is based on SU4 times SU3 gauge symmetry, another has USP4 times SU2 gauge symmetry. And these 2 guys have to be the same. They both correspond to the same type of a theory. And then you can have this TQFT type of expression for the index. Here it is written with all the prefactors explicitly, and all of these things have to be equal. So one can generate a lot of equalities from this geometric thinking of the indices. The derivation of Lagrangians usually is not very systematic, but if one finds these Lagrangians have to match these TQFT expressions for the index. Okay. Finally, before going to the newer stuff that I want to discuss, let me mention also that these Schur indices have a deep relation to very interesting and non-trivial structures in mathematics, to vertex operator algebras, to VOAs. And this was first discovered in this extremely influential paper by Bim, Lemos, Liendo, Pillars, and Rastelli almost 10 years ago. So in any n equal 2 theories, one can identify or one can associate to any n equal 2 theory certain VOA, certain 2-dimensional VOA, and the Schur index can be thought of as a character of the vacuum module of this VOA. And this can be generalized to other modules. One can compute characters of other modules. In particular, one can relate all this stuff to computation of Schur indexes in presence of surface defects. And here there is a very explicit relation between these index computations and the SL2Z symmetry that I mentioned before. And the basic observation, which was crystallized in this paper by Bim and Rastelli 5 years ago, is that if you compute the index, the index that we have discussed before, and indices in presence of surface defects, all of these objects, you can think of them as forming a vector which transforms to itself under modular transformation. So the index itself, the index that we have discussed till now, doesn't have any simple modular properties in this context, but it is part of modular vector. So this is one very particular and very useful way of thinking about modular properties of these Schur indices. They are part of a modular vector, and the index is just a component, and that's why modular properties are a bit obscure. Okay, again, I will not discuss this point of view in detail, but it is tightly related to what I'm going to discuss soon. Okay, so what we are going to try and perform is take these Schur indices of various theories that we have discussed till now and find a nice basis to expand this index in some special functions. We will guess some special functions, and we will try to expand the various indices in these special functions. And we will see that there are very simple, finite expressions, very explicit expressions that one can obtain. And since we are also interested in modular properties, we suspect that these indices should have some interesting modular properties. We will try to expand these indices in functions which have nice modular properties. So the functions that we will consider are the vanilla, very, very standard Eisenstein series. So they are defined using these infinite sums, where these B's are Bernoulli's numbers. And these Eisenstein series have this very explicit, very simple modular transformation properties. So here we take k greater than 1, and for k greater than 1, we have these properties. So we can expand any modular functions in terms of this function C2k. In fact, it only suffices to look at E4 and E6, and everything else can be generated as polynomials in this E4 and E6. And here is an example. However, for our purposes, we will see it will be also useful to look on the more general definition of this Eisenstein series. So here there is this definition of E2k, and I mentioned that E2k for k greater than 1 has this very neat modular property, and for k equals 1, actually this Eisenstein series E2 also has very interesting properties. It's not really modular. So this would be a really modular object, but here there is this funny piece that a modular transformation generates. Okay, and in fact, one can make this E2 to have simple modular properties by adding to it a non-holomorphic piece in tau, where tau, I remind you, we have written this Q as e to the 2 pi I tau. So tau is the norm of this, is hidden in the definition of this Q. So giving up holomorphy of this function, E2 of tau, as defined here, is a holomorphic function of tau. We can obtain an object which has nice modular properties. And for this reason, this E2 object is called a quasi-modular form. Okay, and it will be an important block, an important building block of what I'm going to tell you about. Okay, any questions till now? Okay, so what we are going to do now, we will take these indices of geometric n=2 theories, where by geometric n=2 theories, I mean theories with n=2 supersymmetry that we can obtain by starting from 2,0 theory and compactifying it on a Riemann surface. So we're going to take those theories, use the TQFT expressions for the index that we mentioned before. And here I introduce the overall factors very, very explicitly. And we will try to expand them in terms of this Eisenstein series. Okay, so we will start from the case of A1, where we take the A1 2,0 theory in 6 dimensions and compactify it on a generic Riemann surface of genus G and S punctures. In this case, actually, all of these theories have a Lagrangian description, and we can write matrix model expressions for their indices, but we worked with these TQFT expressions. All these matrix model expressions have to be equal to these TQFT expressions. And what we do the following. We pull out of this expression, this is the index, a certain power of the Dedekind's eta function. And the power is naturally suggested by this overall factor which appears here. And then the leftover function we call P of 1 of GS, where this one stands for A1. And then we try to expand this P1 in terms of Eisenstein series. And we do this experimentally. I mean, what we did, we just computed these indices and we tried to expand them in terms of the Eisenstein series. And for us, miraculously, but as I will mention in a couple of slides, it's not so miraculous. There are very simple expressions in terms of Eisenstein series that you can write. For example, if you take compactification on genus 2 surface, the index is just some constant plus this second Eisenstein series divided by 2. This is this factor P. So to obtain the index, you need to multiply this by this Dedekind eta function. If you go to genus 3, then the expression is very similar. There is some number, there is this E2, and there is an E4 that appears. You go to higher genus, to genus 4, again, there is a constant E2, E4, and now there is an additional factor of E6. So, and you can continue this, doing these computations for higher and higher genus. You can also consider adding punctures. For example, here is a sphere with 4 punctures. This is the theory we already mentioned several times. So this is the matrix model expression for this index, and it has this TQFT type of expression. And now we have an expression for this object in terms of Eisenstein series. So this is given like that. This expression actually was known way before our work. For example, people who studied these VOAs, Chris Beam and collaborators Sarakawa and other people already knew this expression long ago. Okay, so again, however, the interesting thing is that the E2, this quasi-modular Eisenstein series, appears together with E4 and E6 written here. And the really nice thing about this A1 geometric theories is that we can actually write a very general explicit formula for all of these indices, okay? For example, if you take compactifications on genus G surface with no punctures, it has an extremely simple form, which is one can really guess from the several explicit examples that I have written here. So you can write the index of the genus G theory as a sum of first G Eisenstein series. So where for the case of 0, we have just a constant. And then there are some certain numerical coefficients that I will mention in a moment how one can fix. Okay, so there is this explicit simple evaluation formula for all of these integrals. Again, it's not elliptic hypergeometric integrals. These are much, much more simpler integrals. Now, even for other cases, if you look on theories with punctures, so for example, if the number of punctures is even, again, one can write very explicit expressions. The new feature which one obtains when one introduces punctures is that there are these derivatives that appear. So not only, you don't only sum over Eisenstein series, you sum over derivative of Eisenstein series, but the ansatz is extremely simple. So these derivatives are Q del Q type of derivative that you need to introduce. You can generalize this also for odd numbers of punctures, but for odd numbers of punctures, these Eisenstein series that I have defined are not enough. These give you only expressions which have integer powers of Q in their expansion. When you have odd number of punctures, you have half integer powers of Q, and for that you need additional set of Eisenstein series, which are called the twisted Eisenstein series. I don't want to clutter too much the notation, so but one can write expressions for those also. And finally, as promised, these coefficients which appear here, again, experimentally, we don't know why, but they're extremely simple. They are fixed just by demanding that these expressions that are given here, when you expand them in a Q series, certain number of first coefficients given here vanish. Okay, and the first non-vanishing coefficient is equal to 1. So making this demand, fixes these coefficients AI, and whatever these coefficients become is exactly what is needed to match with the topological expression, this TQFT expression for the index. Okay, so let me summarize these observations. So in these cases, in the case of A1 compactifications, as I mentioned, there are well-known integral expressions for the index. So in a sense, if you wish, we obtain a closed form evaluation expressions for all of these integrals as finite sums of Eisenstein series. And moreover, we know also how explicitly to fix the coefficients in these sums. All of these expressions, so let me be more careful. Typically, these expressions involve this quasi-modular form E2, and only the first power of this E2, as one can see here. So these expressions are quasi-modular, but on top of it, they don't have simple modular properties because they are sums of forms of different weights. So here it is weight 0 and weight 2, weight 0, weight 2, and weight 4. So these are objects which have mixed, in a sense, they're of mixed weight. They're different, they are built from modular objects with different weights, but nevertheless, of course, once you write these objects like that, you can study modular properties of these things. Okay. In this case, where you have the 4 punctured spheres, the both objects have same weight. However, this is a quasi-modular object, as we have discussed. Now, the important thing, and here is the reference to this very nice paper by Pillars and Pan. So we have discovered these relations by doing some experimental mathematics, but Pillars and Pan actually took the matrix model expressions for the indices of these theories and, did the hard work of computing them and obtained these types of expressions. And in fact, they obtained something more. So for when you have punctures, you have also symmetries associated to the punctures. So they have derived expressions for these indices, which actually also depend on fugacities for these symmetries. So in this particular case of A1 compactification, there is a proof of this expression. There is no proof, as far as I know, for this simple algorithm to fix these coefficients. So it will be very interesting to understand how this simple algorithm to fix the coefficient can be derived in this particular case. Now let me go to the A2 examples. So A2 genus G generalization of what we discussed. So I will leave punctures aside. So in this case, as I already mentioned, we have at least 2 Lagrangians for the 3 punctured sphere, the Lagrangian discovered by Zafrir and the Lagrangian discovered more recently by Iñaki and friends. So all of these theories also have a Lagrangian description, albeit these descriptions are in terms of n equal 1 Lagrangians and not n equal 2 ones. But again, we can use these Lagrangians to compute the indices that we want. Whether to call these theories completely Lagrangian or not is a debate, and if you want, we can debate that. But there are integral expressions for indices of all of these theories. And as I mentioned, there are also TQFT expressions for these indices. These always exist. And again, what we do, we take this index, we pull out certain factor of Dedekind data function, and then we try to fit to find an expression for this for the remaining part in terms of Eisenstein series. So here are again some results. So for genus 2 theory, we have this type of an expression, and here a new object appears. So before we had E2, E4, and E6. This is something which already appeared for the A1 case, but in this higher rank generalization, the A2 generalization, E2 squared also appears, and it typically for compactifications of A1 2,0 theory, we will also have an E2 squared. So here is a genus 3 compactification and the expansion of the index, an explicit evaluation of the Schur index in terms of Eisenstein series. And again, we have E2s, we have E2 squares, and we have various other objects which appear. Here also we can generalize, we can explicitly compute, perform this computation for various types of genera, punctures. Here we have more than one type of puncture, so we can perform these computations. We don't have a nice expression, closed form expression like this, like some general answer for all the cases for A2 as we have for A1. We have some ideas of what is the structure of the general expression, but this is something that needs to be understood, and we don't know how to write a very general expression or closed form expression with all the coefficients, how these coefficients are fixed for this A2 case. And we can continue this story. For example, we can go to the A3 compactification. In this case, for really a minority of theories, a Lagrangian is known. For example, here is an index, or this non-trivial part of the index for a genus 2, a compactification of A3 theory, for which we don't know any Lagrangian. So only the TQFT type of expression is known. And using it, we can compute this explicit form of the index. And as you can see here, the E2 to the 3 object appears, and the rest of the objects are as in the previous cases. So when we increase the rank of the 6D theory, the power of the E2s that appears in these expressions also increases. So in this pattern, we can see for our other cases also. Okay. So here some comments. So till now we have discussed conformal and equal to geometric theories. Okay, and again by geometric theories I mean theories which can be obtained in this starting from 6 dimensions and compactifying on a Riemann surface. And for all such theories, when we try to find an expansion in terms of Eisenstein series, we found such an expansion. However, it is not clear whether any n equal to theory and index of any n equal to theories will have such an expansion. For example, there are theories like n equals 3 theories that people have discussed and obtained Schur indices for them. And it's not clear whether they have such an expansion. We tried to expand them in the Eisenstein series, but didn't find any useful or simple expression like the ones I have shown before. So it is, yes, sure.
In your higher rank examples,
yes,
or the punctures, which type of punctures did you have? So there
are
any
types of punctures.
Any types of regular punctures.
Any types of regular punctures. Sorry, I need to stick to regular punctures. So yes, only regular punctures. So minimal, maximal, the expressions become more complicated. If you have punctures, you need to introduce other types of, like you need to enlarge your basis, like not only the C2s, but also twisted T2, twisted the Eisenstein series, and some theta functions are also useful. But anyway, there is some finite base, some very simple basis that you can use and expand everything in terms of them with regular punctures, and you always seem to get finite expressions like that.
Thank you.
With irregular punctures and say twisted compactifications and n equals 3 theories, it's not so clear. It's not clear that you can do that. There are some cases that we could not that we could not write in such a simple way. So there is this open question whether these expressions that we have, why do we get them only for these simple compactifications with regular punctures? Given a theory for which we can expand the index in terms of Eisenstein series, does it teach us something about 6D? Can we kind of neatly extract the geometry from this expansion in terms of Eisenstein series? So this is basically what is written in these comments here. Okay. So finally, in the last 5 minutes or so that I have, let me mention that this story can be actually generalized. So I believe it should be generalized. So till now, we discussed only conformal theory. So we focused on geometric conformal theories with regular punctures, and that is a good point. And there is a question of generalizing it to conformal theories, to other conformal theories, the ones that we don't know the 6D origin of, the ones we know 6D origin of, but it is weirder, like theories with irregular punctures. But it is interesting that we can define this Schur index, n equal to Schur index, also for Lagrangian theories, for example, which are non-conformal. For example, an example of a non-conformal theory is just an SU2 n equal to SQCD with number of flavors which is less than 4. And this was, for example, discussed in this very nice paper by Cordova, Gayotto, and Chao, actually in a series of papers which started with a paper in 2016. Okay, so we can define this computation. It actually has a lot of nice properties. It relates to wall crossing phenomena and so on. But here, let me just mention that you can compute these indices. So you can think of these indices again as a matrix integral where you have an integrand which is given by some product of theta function. So it's some modular, some Jacobi form of with some types of properties. And you can think of the computation of the index as computing the zeros Fourier mode of this integrand. So you have this parameter y, and you just integrate over it. Now, why I mentioned that it is a zeros Fourier mode, I did not mention it before. Well, now you can generalize this computation and try to compute other Fourier modes. For example, you can introduce this character. In this particular example, we are discussing a character, some arbitrary character of SU2 labeled by this lambda. So physically, what this means, we are computing Schur index in presence of line defects. Till like at some point in the middle of the talk, I mentioned briefly that in presence of surface defects, the Schur indices form a vector valued modular object. But here I'm considering introducing line defects. Okay, and it so happens that these types of indices, when you look on the different types of line defects that you can introduce, they also form a modular object. And there is something which is called the index of this Jacobi form that you can define. It basically is related, like if this y is equal to e to the 2 pi I zeta, it tells you how the phase of this object behaves if you take zeta to zeta plus tau. So it is determined by some integer. And when you compute this integer for this particular phase, you find that it is actually related to the beta function, which is for minus NF. So in fact, what you obtain a modular object, the size of which is related to this index of the integrand of the index. This is different index, and that's why I wrote it in italic here. Now, when you look at what you obtain, it's actually really modular only for an f which is smaller than 2. And what happens for an f which is smaller than 2? This object is actually regular. It doesn't have any non-trivial poles in y. Okay. It has no poles away from the origin. And if this integrand doesn't have these non-trivial poles, it is a mathematical statement that these Fourier coefficients of the modular forms form a modular object, a modular vector. And again, the size of the vector is related to 4 minus NF. If this integrand has poles, you also obtain a vector valued modular object, but that vector valued modular object is not simply modular, it is mock modular. And the technology of this mock modularity, exactly of this type of mock modularity, was, for example, discussed, of course, by Zwegers in his thesis and by Dabolkar, Murthy, and Zagier in the context of black holes some time ago. So if you look on non-conformal theories and their indices, this quasi-modularity property actually becomes a mock modularity. And the conformal case of n equals 4, this index, this beta function vanishes, and it is a special case where these mock modular properties, in a sense, degenerate to quasi-modularity. But maybe if we want to understand this modular property and expansion of indices in terms of modular objects, we need to go to this more general realm of mock modular forms and various types of mock modular forms of various depths and so on. For example, here, the index is given by a single integral, but when you consider non-conformal theories of higher rank, you will have multiple integrals. So you will integrate Jacobi forms, like you will consider Fourier coefficient of this Jacobi form, and then a Fourier coefficient of a Fourier coefficients, and so on. So you will have some nested type of structure of mock modularity in general. And the physically interesting question here is, of course, whether from this modular structure we can extract any interesting physics. So what comes with mock modularity is something which is called a shadow. Mock modular object is an object which becomes modular if you add to it some non-holomorphic piece in a very particular way. And for example, an interesting question is whether there is any physics in that correction that you need to add to the index. So I'm running out of time, so let me summarize. So we have discussed the very explicit evaluation formulas for the Schur index of a very large but very concrete class of geometric n=2 CFTs. And again, this corresponds to compactification of Riemann surfaces with regular punctures. These formulas exhibit very intriguing regularity, which we not really understand. So the interesting question is, what is the physics of that regularity, and can we make explicit statements about it following from geometry? Again, I emphasize in the end that maybe to really understand this structure, we need to give up these conformality considerations and consider generalize this quasi-modularity to mock modularity and so on. And two more speculative directions, I believe these questions probably should be answered. They might, answer for these questions might exist already in math literature, and which just need to interpret the answer physically. I'm not sure, but maybe it is there. But there are two more speculative questions that one can ask. So I mentioned in somewhere in the beginning of the talk that there is this n=1 generalization of Schur index. So is there any interesting modular structure there? Okay. Another, of course, question, the big question is whether, say, we understand the modularity of this structure for the Schur indices, and that is related to the group SL2Z, how to generalize and whether it generalizes to the realm of the full elliptic integrals that we have. Can we find a basis of functions which behave nicely under SL3Z transformations, whatever that means, in terms of which we can expand these integrals into explicit evaluation formulas? Okay, and let me end with this. Thank you very much for your attention.
Yeah, thank you very much, Shlomo. Please, questions? Slava, do you have anything? No?
I just have a question about turning on the flavor fugacity. How far can we go with the flavor?
So this we didn't try to do. So this is this I will refer you to this paper by Pillars and Pan. Mm-hmm. So they could, for A1 cases, they could find very explicit expressions with flavor fugacities. Mm-hmm. Beyond A1, since they considered n=2, explicitly n=2 Lagrangians to do their computations, I don't think they can go, beyond the A1 case. I don't remember whether they had some results for, Lagrangian higher rank cases, but. They use the integral expressions to make their computations, and you can try to find expressions using these TQFT types of expressions, now refining them. This is only for genus G, but you know, here you can have also puncture. So basically you need to refine with the fugacities for flavor symmetries and see whether you can understand, you know, what is the basis of functions in terms of which you can expand also for higher rank cases, and what type of structure you obtain. It will be a very interesting question. And yeah, I don't know what will be the best, you know, I think there are many questions here. And, you know, my feeling is that, you know, refining with flavor fugacities should be complicated, but maybe I'm completely wrong. And maybe that's the thing one should do first. And everything else will follow from it. I don't know.
Thanks. Other questions? Okay, I didn't hear anything, so thank you very much, Shlomo. So that's it for this section, and then we'll come back again at 5 p.m. for David Gayota's talk. Thank you. Bye, see you later.